what is the acoustic uncertainty principle? This principle basically describes a trade-off when you're trying to measure the energy distribution across time and frequency. If you want to describe a sound signal, which is sound wave, and you want to know where the energy distributes across time and frequency, if you want to be very precise in terms of timing, then you lose information in the frequency domain. And vice versa, if you want to know exactly which frequency the energy is concentrated, then you can't really be quite sure how the energy changes over time. So let's imagine you have a signal which is exactly 5 Hertz. Okay, so that's like, I'm just going to draw it in a not very nice way. This is 1 second. Is it five cycles? Around about 5 seconds. You get the idea. So this is 1 second, and you have 5 cycles. Okay. And in order to observe that energy at 5 Hertz, I need to look across the entire 1 second period to know that. Yeah. And then of course, if I take a longer view, so if I have 2 seconds, then I know that, okay, there are exactly 10 cycles within that 2 second period, and I know it's still 5 Hertz frequency. Okay, but if you want to take a smaller window, let's say 100, break it down, yeah? 5, okay. If you take a 100 milliseconds window, okay, we just observe that period, and all we can observe is something like this. There's no cycles, it's like incomplete cycle. Then we don't know what the frequency is just by looking at that, because it could well be the signals continue to extend, and it could be something like this, which is more like 1 cycle, or it could be something like this, or it could be a very high frequency thing. It could be something like this, but we don't know. We only have that incomplete picture over here, right? So even though we can get a reading every 100 milliseconds, is essentially, if you have a short time window, you will have a reading every 100 milliseconds. So if there is energy changes at a time scale of 100 milliseconds, you will know, because you take a reading every now and then. But you're not quite sure exactly where the energy is distributed. It could be 1 Hertz, it could be 10 Hertz. We don't know, because we only have this much information to estimate what kind of where the energy is concentrated in terms of frequency. But if you want to be sure about the frequency domain, if you want to be more precise in the frequency domain, then you want to use a long time window, so you can observe the oscillations over a long period of time, so you can count how many cycles it actually occurs, let's say over a second. But the downside of that is you only take 1 reading every second. So that's why if you want to be more precise in terms of frequency, then you're going to lose information in terms of time, because you need time to get the frequency right. Okay, so you have only two readings over a 2 second period. Whereas if you use a 100 millisecond time window over a 2 second period, you have 20 observations, but not very accurate observations in terms of frequency.